So, I welcome all of you for this last session of the winter school on planetary science. And uh, I welcome today's speaker, uh, Deepak Kumar Sahu. So, uh, let me introduce it for people who were not there yesterday. Uh, so, Mr. Deepak Kumar Sahu is currently the HOD of Geology, KJ Somaya College of Science and Commerce. He has done his graduation from Ravenshaw University, Cuttack, and his post-graduation from University of Delhi. After that, he has worked in the industry in a company, Data Private Limited, and then he went on to join the Xavier's department, and finally he joined the Somaya College Geology department. He is about to submit his PhD thesis on the topic of igneous petrology from Savitribai Phule Pune University. His research interest is in understanding uh, magnetism in trans-Himalayan orogeny. He has presented many papers in national and international conferences. He has authored some books, uh, and one of them is Engineering Geology for Civil Engineering Students. Okay, so I welcome Deepak to go ahead with the session. So,
Thank you, Shekhar sir. Thank you, Mahesh sir, uh, giving another opportunity uh, to speak with students from a winter school. So I hope let me share my screen. I guess everyone has enjoyed the previous two lectures, and this is again after a lunch session. So I hope everyone has. I guess like most of you guys are students, and definitely you are also enjoying your vacation with the lecture series. So you might be not very sleepy. Okay, so those who are a bit sleepy, they can sit with a cup of coffee or tea. Okay, so today actually I will be talking about how the magnetic anomaly helps us in mapping the sea floor. Okay, so we generally uh, call them as magnetic tape recorder because they are the one who tells a lot of story about the plate motions. Okay, so coming up with a slight background and history, how how does this hypothesis, how people started actually thinking about uh, this magnetic anomaly, which help them in mapping the entire sea floor with with the dating of the sea floor. Okay, so already I have spoken about how we do dating, relative as well as absolute dating, in my last lecture. So moving ahead with just a brief idea about what is uh, continental drift. Just give me a second, like I just don't want few things. Yeah. So is my slide a bit clear now?
yeah,
Yeah. Okay. So the entire mapping of the sea floor, okay, came up with this idea of continental drift. I guess like everyone knows what is a continental drift is, how this hypothesis came. Okay, so uh, uh, you can see like the continental drift was was a big debate during this 16th century and 17th century, when some of the European scientists, they noticed that there is a jigsaw puzzle which fits the coast of South America and Africa, uh, and the coast on the sides of sorry, the America, Africa, and Europe were sometimes like as a single part, which we can see in the figure as well. Uh, एक, एक minute, Mahesh sir, we used to get a laser point, right?
So if you can right click on and go to the pointer option,
Okay.
right click on the slide. I, you are not using PowerPoint, right? It is, I
Yeah,
think,
I'm not using PowerPoint.
okay.
Let me figure out.
Or
Uh,
you may choose a pen and mark.
Use
uh, this a note, and then I think. Just a minute. Actually, my screen is hanged for a minute. Let me check what I can do. Okay, whatever it is. So, we'll go this way.
or
See,
maybe you can switch off your video so that there's no issue. And you can use the mouse pointer if you.
yeah, 1 minute. Sorry. So, uh, yeah, so it's all started a very long back in in 16th century and 17th century, when the scientists thought ki there is a jigsaw puzzle on the sides of Atlantic Ocean, where they could find that the America and the African continent and European continent in some period of time long back, it must have came together and were a one single landmass. Okay, so this puzzle, it was later on was well studied by Austrian geologist whose name is Edward Swiss. and he said, he postulated his hypothesis that the present day southern continents, okay, the present day southern continents uh, had once formed as a single giant continent, which was called as Gondwana land, or just a Gondwana. Then in 1951, there was a breakthrough by this German meteorologist Alfred Wegener. He uh, he was actually he was in the World War I, and he was healing from the wounds which he got in World War I. During that time, he wrote this book on breakup and drift of continents. So he said that there is a similarity of rocks and some of geological structures and fossils on the opposite sides of the Atlantic. So this was a very big hypothesis, which created a big debate between geologists as well as physicists. So Wegener, in his hypothesis, he po- he said that there is a supercontinent which he called uh, Pangaea, which in Greek term it is known as all lands, and that broke up into the continents which we know them today as as Asia, Europe, Africa, South America, North America. So, but his hypothesis about how fast these continent moved and what was the forces that has pushed this continents from a single land mass into a different continents was a big debate, and he couldn't able to prove it because no one got convinced with what he was explaining about the that all the continents were together once upon a time. So this debate went for a decade, and then the physicists, they convinced that the outer layer of Earth is too rigid, that the continent drift to occur will be very difficult. And this somewhere the hypothesis of the Wegener talking about plate movement or continental drifting uh, was not accepted, except few people who thought this might be possible because some of the fossils which were on both the sides of Atlantic were same. It could be only possible if the land is somewhere close or together, because Atlantic Ocean is a huge ocean. How some organism may migrate from one place to another place if they are not marine for organisms. If they are in the land part, how they could able to migrate. So these were like few thoughts, okay, few thoughts which triggered people to think about what could be the driving forces for these continent to move. Then sir, can I stop and rejoin again? Even
Okay, sir. Yeah.
my slide is also not moving.
Fine, fine, sir.
Okay, okay.
Shubham, you have paused the recording. Please.
Can you just yeah. So then in 1928, this British geologist Arthur Holmes, he proposed that the convection current in the mantle, the upper mantle, would be the source for the for the driving of the lithospheres. Okay, so he suggested that like how we boil the water in a vessel. So what happens is like the boiling water moves as a convection current. So the hot water from the bottom, it rises up on the top, and when it cools down when it reaches the top, and again it goes back, or it sinks down to the bottom of the vessel, and again when it warms up, and again it rises again. The same concept he explained, and he said ki even in the mantle, the hotter material, the hotter matters in the mantle is to rise because of the high temperature, causing the plate to form and diverge. Okay, so when they diverge, where the plates usually get converged, that's the where they cool down, and they are again falls down or sink down to the mantle, and again when they warm up, they rise again. So this was the concept which was given, and worldwide people started agreeing with this concept of mantle convection would be the driving forces from where the plates started moving apart or drifting apart. So again, the hypothesis of Alfred Wegener on continental drift started. People started looking again into that concept and started studying more about it to get a more proper results which could prove the hypothesis. So that is the time when people started thinking about the sea floor spreading. Okay. So when they came to know about this convection current must have, drifted the continental plates. So the scientist from Princeton University, Harry Hess, in 1960, and along with him, Robert Ditz of Cripp Institution of Oceanography, they proposed that the crust is to get separate along the rift in the mid-ocean ridges, and that the new sea floor is to form by upwelling of the hot new crust into these cracks. So in the figure, if you see on the first figure, it's a North Atlantic Ocean floor. You can see a ridge of mid-oceanic ridge has been created at the middle of the ocean, Atlantic Ocean. Okay, it shows a crack-like rift valley, which is running down the center of this mid Atlantic ridge. Okay, so on the next figure, that is the Pacific Ring of Fire, where people started thinking about with this particular hypothesis ki, uh, I think someone has unmuted. So, students, you can mute yourself. Yeah, so this hypothesis of spreading along the mid-oceanic ridge, created a new idea on in physicists as well as in geologists. They started thinking about ki, somewhere even Earth is expanding. Okay, because a new ocean floor was created along this ridges because of this mantle convection current. So as the mantle plume is to come up and divert the plate boundary, making a crack, making a rift. Along the rift, the new ocean floor, ocean plate will be covering the gap. Okay, so that means like people started thinking ki there would be new ocean floors which will be created, and the lithosphere started expanding. but it was not the case. The You must have in the first lecture you must have heard about Wilson cycle. So in 1960, this person Wilson, he said ki there is always like a new ocean basin is to be created along this mid-oceanic ridges, and it is to get converge. Okay, so somewhere the ocean lithosphere was also getting destroyed at some other part of the earth. So it cannot be happen ki every time there will be expansion of the lithosphere. So you can see in the next figure, the second figure, where you could see the specific ring of fire. We know that this specific ring of fire is all about active volcanoes. Okay, so this red dots, which you are seeing in the image, is the active volcanoes, and the black dots which you are seeing are the earthquakes. Okay, so this entire region is again a very active tectonic region. So where the plate is getting subducted, where subduction means one plate is going beneath the another plate. So at one part of the earth, the plates are diverging, creating a new ocean floor, and at another part of the earth, they are diverging. Sorry, they are converging, and one of the plate is getting destroyed. So this was a concept which leaded to make to understand the lithosphere, and people divided scientists divided Earth's this lithosphere into some major 13 major rigid plates, along with there are some sub plates as well, smaller plates as well. So you can see like in this map, the red color arrows, okay, they are showing you the divergent plate boundaries. Okay, and then the blue color arrows, they are showing the convergent plate boundaries, and the yellow ones are the transform fault boundaries. Okay, and the numbers which you can see in the next to the arrows are nothing but these are the speed of the plates, or the velocity of the plates, which is given in millimeter per year. Okay, so this is how the entire in the globe we could see different plate boundaries. And the major plates are like Eurasian plate, North American plate, your Indian plate, your Australian plate. Okay, there are some sub plates like Somali sub plate. Okay, so these are this is how the entire lithosphere, which is composed of both continent as well as ocean, has been divided into different plates and their movements. So if I go like these plate boundaries, okay, these plate boundaries uh, are dependent on what type of lithosphere it is and what are the diving forces. Okay, so the divergent a boundary are by forces which is pulling apart into different directions. Okay, so we have like three different plate boundaries uh, for a lithosphere. That is your divergent plate boundaries, your convergent plate boundaries, and your transform fault boundaries. So, uh, in divergent plate boundaries, you have a plate a lithospheres of two oceans which are diverging. Okay, when two ocean lithosphere diverge, like for example, here in this figure A, if you see, it is the North American plate and the Eurasian plate along this mid-Atlantic ridge. Okay, so these two plates are diverging, creating this mid-Atlantic ridge, a rifting, and there is like small multiple chains of volcanoes, or you can say ocean mountains are created because of these rifting between these two ocean plates. That is your North American plate and the Eurasian plate. Same way, you will be seeing a rifting even in the continental plates. Okay, continental plates are more rigid than the ocean plates. But ocean plates are a bit high in density than the continental plates. The density is again because of the composition. Okay, so we also see divergent plate boundaries in the continental lithosphere. Okay, so what happens in continental lithosphere? The example is like very active, okay, rifting which is going on in Africa, the eastern part of Africa. So this is the example of Eastern Africa, which we call it as East African Rift Valley. So you have African plate and your Somali subplate, which is diverging. Okay, because of the divergence, there is this East African Rift Valley has been created. Okay, which is a parallel valley in a zone with numbers of volcanoes and earthquakes. So again, like if you will search in Google, you will find many active volcanic eruptions on the northeastern part of your Africa. Take it example of Libya, okay, where this rifting is going on. So you can search, like there are many active volcanoes along this rift valley, and people are, the scientists are in this view that there will be a new ocean basin which will be created after many years. After many years, there will be a new ocean which will be created along this East African Rift Valley, where the northern part of the Africa will get separated from the southern part of the Africa. Okay, then comes your convergent plate boundaries. Okay, you will see convergent plate boundary again in three different lithospheres. One is your lithosphere, one is ocean continent, and then continent. So the ocean convergence, the very good example is your Mariana Trench. Mariana Trench is the deepest part of the earth. Okay. So here what happens is the two plates will converge, means there will be a compressional forces where the forces are towards each other. In the divergent plate, they were moving away from each other. Now they are coming in the same direction. When that happens, they collide. The lithospheric plate, which is of high density, okay, relatively high density, will go down the a plate which has low density. Okay, so that creates your Mariana Trench. Here the plates are Philippine plates and the Pacific plates. Next is your ocean continental convergence. So here, a very good example is of Andes Mountain in the South America, in the Peru-Chile coast, which is again one of the largest mountain chains after Himalayas. So what happens here is you have one oceanic plate and a continental plate. That is, your South American plate is a continental plate and your Nazca plate is your ocean plate. When that converge, your ocean plates are always high density than the continental plate. That converge, they create this Peru-Chile trench at the axis of collision, and in the continental part, they create this Andes mountain. Okay, this is one way of mountain building process. I guess in the morning lecture, you must have studied already about the mountain building process. So I'm just giving you a brief idea again about the plate boundary. Next is your continent-continent convergence, which creates the Himalayas. So here, both the plates are continental plate of same density. Okay, so since they are of same density, some of the part it comes rather than going down, it comes above, creating a very a big and very high altitude uh, folded mountain belts, which we call it as Himalayas. Okay, same way you have this transform fault boundary, and again you have transform fault boundary in the mid-oceanic ridge as well as in the continental transform fault boundary. So this ocean may you have along this Atlantic mid-oceanic ridge where you have this North American plate just sliding over the Eurasian plate. So here there is no divergence. This plate boundary, it doesn't create any ocean plate, any new ocean plate, nor it destroy any ocean plates. Okay, so here there is only what happens is they just slide with each other, and it creates many earthquakes because of this sliding. So most of our earthquakes usually forms along this transform fault boundary. They are very all these plate boundaries are prone to earthquakes. Among this, the transform fault boundaries are the ones which creates more and more frequent earthquakes. So moving ahead with so I hope like everyone has got or revised the plate boundaries. Okay, so now the question comes, how fast do this plate move? Which was the the question in the beginning itself. I said that was one of the question by every scientist, be it a physicist or a geologist, to understand how fast these plates are moving, and whether some of the plates move faster than the others, and is the velocity of the plate movement today is same as it was in the geologic past. Okay, so this is the important question. So this questions was solved by the magnetic anomalies. Okay, so now what is magnetic anomalies? So during this World War II, people used many sensitive instruments where they try to detect the submarine by the magnetic field which is emanating from their steel hulls. So the geologists, what they did is they modified these instrument slightly, and then they towed this instrument below the research vessel, and they tried to measure the local magnetic field which was created by the magnetized rocks which were beneath the sea. So when they saw like they actually put the magnetometer. Okay, magnetometer is an instrument which detects the magnetic field. So they found that there is a regular pattern of high field magnetic as well as low magnetic field. Okay, so that regular pattern they could see when they were moving. Okay, they were moving along the Atlantic Ocean from one coast to another coast of Atlantic Ocean. Okay, so so these alternate high and low values of magnetic field, they call it the as magnetic anomalies. Okay, so you can see in this picture this this colorful bands. alternating colorful bands are your magnetic anomalies, okay, which are almost symmetrical with respect to the axis of the ridge. So if you see the axis of the ridge, the line which has been drawn, axis of the ridge, you see on either side of the ridge, you will see the banding, the color banding on either side of the ridge to be placed exactly at similar distance from the center of the ridge. So that's the reason why they are saying that it is perfectly symmetrical with respect to the crest of the mid-oceanic ridge. So this something could the people started thinking about why there is high magnetic field and then a low magnetic field. So what could be the reason, like whether people were knowing about the rock which is beneath the ocean floor, or which consists this ocean floor, are somewhere magnetized so that they are getting these differential pattern. So for studying about these magnetic anomaly, then the first uh, ocean drilling project started. People, and the research vessel, they put a drilling machine below the seafloor to collect the rock sample. Okay, so we get as a core samples from below the sea floor, and they started, looking into the rocks, okay, and studying like how the magnetic deflection could be, is seen in the entire pattern. To a better way to understand what, let us first understand what is magnetic field of the earth. This is a very basic thing, I guess, like as a physicist, you guys definitely might be knowing about the magnetic dipole movement, and the magnetic field of the earth. Okay, so the magnetic field of the earth is very, very similar to like a magnet bar. Okay, so if I want to understand how does the magnet bar, the magnet bar may, the magnetic field is being created, I just need to put some iron pins in a piece of paper, and at the middle of the piece of paper I will put a magnetic bar, and I will spread these iron pins, and when the magnetic field will be created, they will start moving, or they will align in a proper north south ka alignment mein, from where the magnetic field actually forms. So same way, the scientists have proposed कि if you keep a very huge, giant magnetic bar at the center of your Earth, okay, so it will also create similar kind of magnetic field. Okay, so but there is a slight inclination of this magnetic field with respect to your geographic north. So there is a 11-degree ka inclination which has been seen between the geographic north pole and the magnetic north pole of Earth. So the question comes like from where this the magnetic field is being created. So these are the liquid core. Okay, so the liquid core, the core ka composition is 99% iron and nickel. Okay, so this core actually creates this magnetic field which comes from the mantle plume, and then it it spread all over the earth, what we see as a magnetic field. So taking this principle, people started understanding in the volcanic rock. So now, if you see, this is the normal magnetic field where your geographic north pole and your magnetic north magnetic pole are aligned in the same direction with an inclination of 11 degree. So when people started studying about this volcanic rocks, they contain iron silicates mineral. Okay, so this iron silicate minerals, when they start crystallizing, during the process of crystallization, they some of these elements started aligning with the magnetic field of the earth. Okay. So in early 1960, geologists could able to understand this behavior of no of the minerals in the volcanic lava is to magnetized in the direction of Earth's magnetic field, and this phenomena is called as your thermo-remanent magnetism. Okay, thermo-remanent magnetism. So because the rocks remember the magnetism, which was long after the magnetizing field existing at the time it formed has changed, then it is the reversal. So if you see in the diagram, what happens is the red one is the lava which is coming up. Okay, we call them as conduit, volcanic conduit, from where the lavas are coming up. Okay, or you can say the magmas are coming up, and they comes out of the surface, and then they get deposited along the flanks of the volcano. So they found that some of the layers, okay, because the lava flows as piling of the lava. So there will be one lava flow above another lava flow, then again another lava flow. That's how the lava actually moves on the surface of the earth. Okay, so they found that the rocks of different layers of the lava was giving you a different magnetic anomaly. So one layer gives a normal magnetic field anomaly, another gives a reverse magnetic field. Okay, so that is what is called as your thermoremanent magnetism. So the reversal one, so it the lavas were knowing what was the magnetic field uh, in the past when they got crystallized, and now like the magnetic field is different. So they have already like captured that magnetic field because the iron silicate minerals aligned along the magnetic field of that time period. Okay, so this pattern they could able to see in all the different layers of lava flows, and they found that there is a alternate change in the pattern of the magnetic field with the period of time, with different periods of time. Okay. So they started studying, for many different rock types at different places around the world, and to understand the reversal a pattern of magnetism through the geologic time period. So this, you can understand this helped, the geologists to measure the rate of seafloor spreading. So this is a very a small diagrammatic way. People where I want to explain how this how the scientists started measuring the seafloor spreading. once they know what is the seafloor spreading, they can automatically, you can determine the speed of each a plate. Okay, so there was a oceanographic survey which was carried in Reykjavik Ridge, which is a part of your mid-Atlantic ridge, which is just southward of your Iceland. Okay, so they put this magnetometer below the ship, and they try to move from one of the coast to another coast of the Atlantic Ocean, and they found this alternating bands of your a magnetic anomaly with high intensity and the low intensity. Okay, so then they started studying this volcanic sequence, the lava flows in the the lava flow in the sea floor rocks. So what they saw is one of the layer is giving you the positive, positive anomaly, and the another layer is giving you this your negative anomaly, and the deeper layer are the older ones, which preserve the direction of the magnetic field at the earlier times. Okay, so by determining the age of that magnetic reversal at many volcanoes, the scientists could construct this a magnetic timeline, okay, or magnetic time scale, which you can see in on the uh, uh, right side of the slide. Okay, so they created a time scale from the present to some 5 million years back. Okay, and they no they gave the units as crons for the major magnetic anomaly. And with this magnetic anomaly, which is your one cron, one magnetic cron is generally some hundreds of thousands of years long. But they also found that there are some short reversed event as well. So they gave that reverse event as terminology as subcrons. Okay, so with this magnetic crons and subcrons, they created this magnetic timeline. Okay, so the names which you are seeing here as Brunch's normal cron, which is the present a magnetic anomaly. Then comes your Mathioma reverse cron, Gauss normal cron, and Gilbert reverse cron. So these are the scientists' name who have studied about the magnetic anomaly, and by their name, the cron name has been given. Okay, as Brunk's normal cron, Mathioma reverse cron, Gauss normal cron, and Gilbert reverse cron. So this is how the entire then the sea floor ka timeline is given. So you can see like from 5 million year old or the towards this is your ocean crust, which is today. And then in the middle of the mid-oceanic ridge, that's the place where the magnetic anomaly is zero. Okay, the age is zero. There's the positive ones, okay, which is the current magnetic field, and the rocks are the recent rocks along the axis of your mid-oceanic ridge. Okay, so just compare this diagram with the mid-oceanic ridge, which is is shown in the left, top left side. Okay, so the Bronchus normal cron are the along the mid-oceanic ridge axis, from where the new ocean crust is actually has been created by the upwelling of the mantle plumes. Okay, that's why the rock types along the axis is positive and the age is given as zero. And then as you move away from the axis, okay, away from the mid-oceanic ridge ka axis, you will see that the age of the rock is going older and older. Okay, so from zero, if you see as you move away from the axis, the age of the rock is 0.7. So sometime like on both the sides, okay, of the axis, the age is 0.7, 0.7. So that's the reason why you're getting the symmetrical anomalies. So you're getting like axis may zero, then as you move away from the axis, you're getting older rocks, which is of 0.7. Again, as you move further away from the mid-oceanic ridge axis, you will again see there is a older rocks. The age is given as 2.5. Then again, as you move, you will get an age of rock which is 3.3, which is the border of your Gilbert negative reverse cron and Gauss-ka positive cron. So this is how, like, as the spreading has been happening in the mid-oceanic ridge. A new ocean basin has been created, which the rocks are the magmas when they crystallize. They are aligned, the ferrosilicate minerals align with the magnetic field of the earth if they are not reversed completely. Okay, so there is a 180-degree ka flip, which is seen in the reversal isochron. So there is so you can see like there is a positive, then there is a reverse, then again there is a positive, then again there is a reverse anomaly which has been seen. So by now the question comes how we can calculate the
Sir,
velocity.
one,
Yes.
I'm sorry to disturb, but
Ha.
there is a question about the terminology. So using mouse pointer, if you can describe the magnetic anomaly. So what is the magnetic anomaly, and can you show here? Because
Okay.
your pointer is not visible right now, so
Ha.
it becomes difficult to check.
Yes. Okay. Just a minute. So is my screen is still visible?
Yes, it is visible.
Huh. So the magnetic anomaly here is if you can see this lines which you're getting in the along the axis ridge. So you're getting a very high high magnetic field over here. So as we move away from this ridge, so can I just see? No, I'm not getting the pointer by the right click
No,
as well.
here we can see the mouse pointer.
Okay,
It's
okay, sir.
small, but we can
So
see.
yeah, so as we are moving, this is the mid Atlantic ridge, and as we move just away from the ridge axis, so again we are getting a lower intensity. This is what is called as your anomaly as. So if you see in this image, this particular image, we get these kind of anomaly pattern. Anomaly is
What can you give approximately what units we are talking?
anomaly is like something a value which you are getting a very higher than the background value. Okay, there is something called as a background value where like this should be the no the magnetic number. Okay, but when you are getting something very higher or very lower than the a background value, that is what is we call it as anomaly.
For rocks, how does one measure magnetic? I mean, in what units does one measure magnetic field? Uh,
Sir, is the same Gauss is the I think, unit in which we measure the magnetic field, even in the rocks.
Okay.
Okay, so
So I'm sorry to disturb again, but uh, while talking about the magnetic fields, we learned in one of the lectures that the Earth's magnetic field, if we're measuring in say nano Tesla,
huh,
then that is somewhere around on an average 50,000 to no, 50, around 50,000 nano Tesla. So in terms of that nano Tesla, what are the anomalies, if you can, the order of magnitude may not be exactly, but approximate numbers that it is flipping or it is changing.
okay. Uh, the changing is basically, sir, here, with the value, is like, you have an upper limit and a lower limit. Okay, so the upper limit and lower limit could be any, like you can say like 50 Tesla to be an upper limit, and uh, the or you can say the anomaly limit, and actually it should be a 30 Tesla as the magnetic field, but your
30,000 nano
yeah,
Tesla, you mean?
30,000 nano Tesla.
Okay.
But you're getting something like 50,000 nano Tesla, other than like getting a 30. So that is what is your anomaly is.
Okay, sir.
Okay. So I will continue from like how the speed of this sea floor spreading is being measured. So we generally use the simple formula of speed, which is equal to distance by time. Okay, so for example, you take the boundary between the Gauss normal polarity chron and the Gilbert reverse polarity chron. So the dates which I have mentioned here, that's the time. So this is being calculated by the absolute dating method. Okay, when you collect the rock from the sea floor by using a drill machine or a bore machine. So we do boring and then we collect the core samples from the sea floor, and we calculate the age by using this radiometric dating methods, which we discussed in the last lecture. So you get the age from there. So if you see this Gilbert reverse polarity and your Gauss normal polarity, the lava flow has been dated as 3.5 and is located 30 kilometer away from the ridge crest. Okay, a crest is nothing but the axis ka crest. So from there, it is 30 kilometer where the sea floor have moved towards this North American and Eurasian plate, which has been apart by about 60 kilometers in 3.3 million years. So when you have this distance as your 60 kilometer, you have the time as 3.3 million years. When you divide the distance by time, you will get the spreading rate as 18 kilometer per million year. So if I divide 60 by 3.3, we are getting close to 18, right? So somewhere you're getting 18.18. That is what is 18 kilometer per million years. So your plate, the North American plate and the Eurasian plate, are diverting at a speed of 18 kilometer per million years, or you can say 18 millimeter per year. So that's the speed of the plate which has been getting diverted from the ridge of your Reykjanes ridge crest. From there, the speed, the divergent speed is 18 millimeter per year. This is how we try to calculate the movement of the seafloor. Wherever the seafloor has been spreading or the plates are getting diverged. Okay, so with the help of this isochron, this magnetic anomaly, okay, this is how the seafloor ka mapping has been done using this magnetic anomaly and the age. So here the isochron means equal contour of equal age. Okay, contours of equal age is what is known as your isochron. So this is where like you're getting like different color bandings, okay, which represent a span of time which has been covering the age of the crust within that particular time band. Okay, that is where you're getting this color bands, and the boundary between these bands are nothing but are contours of equal age, and we call that as isochrons. So with that, this red color, where you are getting very dark red color, is the one from where the new ocean plates are being created. That's why it has an very younger age, and it is given as a dark red color. And as you move towards the continents, okay, this is in the ocean. Along the ocean, you are seeing most of the red color ka bands. As you move further closer to the continents, you are seeing the older rock types. So somewhere like if you see the blue patches in the map, they are the one which are the oldest ones. So if you consider uh, this particular part of the ocean, which is the mid-Atlantic ridge, which we are, no, I was giving you most of the example. So as you, see, move along the American coast, you're getting the oldest seafloor basin, and the same thing you're seeing along this, along this European and the African coastline. That again you are seeing this older sequence of the rock types. So this is how we map the entire seafloor using this magnetic anomalies. Okay. So this seafloor spreading played a very, very important role in when we started mapping this entire seafloor basin based on the spreading of this seafloor. This actually helped and convinced everyone to understand the rifting of the continent and the drifting of the continent and the collision which assembled and dispersed this Pangea, which was which we were talking in the beginning of the lecture. Okay, so how I will just summarize you, okay, with this slide. How does this Pangea actually got assembled first? Okay, so during very old time, that is in the Proterozoic, which has an age of 750. It's like just after beginning of the Earth ka crust, okay, to 750 million years. So that is the time period when people found that there was a supercontinent which was known as Rodinia. Okay, so this Rodinia supercontinent, it formed somewhere about 1.1 billion years ago. So our Earth formed at 4.5 billion years, and Rodinia as a supercontinent formed at 1.1 billion years ago. And then it began to break up at 750 million years ago. uh, uh, so these no supercontinent ka study is not only taking evidence of magnetic anomaly. People have taken very different other aspects, all the geological event, dating of the rock, everything. By considering them, they have came up with this evidences. Okay, so during this late Proterozoic, your rodinia started splitting, and at somewhere around the Triassic. Okay, Triassic is the period where the dinosaurs were evolving all over the world. So that is the period when this Rodinia, when they got splitted, they all came together as uh, as one landmass, which is called as Pangaea, as another supercontinent. Okay, then from your Jurassic period, this Pangea started breaking up. Okay, so almost like during this late Cretaceous, that is the time where when this dinosaurs got extinct. So till that period was the time when the Pangea completely started breaking out. And then after that, all the southern continent, India was moving towards the northeastern part, uh, separating from Antarctica, Australia, Africa. And then after 66 million years, the Indian continent also got separated from Madagascar island, and then it's moved further in the northeast direction, and that is what we see today as the present day world. So all this drifting, rifting of the continent, the people knowing about, and they are more like studying about other supercontinent as well. It all came only because of the seafloor mapping, which we could do only by knowing this magnetic anomaly. Okay, that's it. Thank you.
I think we can take the questions. There are a few questions, uh, but some of you want to ask the questions directly, can ask the questions. There are not much questions.
No, people can raise the hand so that we can unmute them. But there are some questions that
Yeah, I
the
mean, there are few
chat.
questions. I think they themselves can just state their name and ask. Otherwise, I'll
So,
read the questions.
no, if you can read because so Hari has raised one. Hari Krishnan has raised hand. So yeah.
Um, Hello. Yeah. So, is Rodinia the oldest landmass that we currently know of, or are there evidences of much earlier, older landmasses? Because in the slide it was like 1.1 billion years ago. So I'm just guessing that's like more.
Yes, there are like older subcontinent, like supercontinent than Rodinia, but you don't have much evidences. So
Okay.
the evidences are lacking. That's the reason why we still consider Rodinia as the oldest supercontinent.
Okay. And could you like okay, which are the sites like locations where uh, we have found the evidence of Rodinia, like the landmass, the rocks or what?
Yeah, so even uh, we call these land masses as cratons. Okay,
Okay, yeah, yeah.
cratons.
Hmm.
So cratons are one of the stable part in the earth. Okay,
Mhm.
so in India also we have cratons, like we have cratons in the southern peninsula. We call it as Dharwar craton. The eastern part we call it as Singhbum craton. So when people started studying and dating the rocks of these cratons with comparing with the cratons of other continents, like from Australia, from Canada, from America. Okay, so when they studied these cratons and their characteristics, from there they found out that these land masses somewhere would be together as one land mass.
Okay.
So
Uh,
recently, there is a no, there is one paper got published which says in Orissa there is a rock which has been dated for 4.2 billion years ago. Okay,
4.2. Oh, okay.
4.2. Okay. So currently, like we are like most of the literature, if you find it will say like the oldest rock to be of 4 billion years ago.
Yes. That's true. I have another question related to uh, like measuring the uh, the studying the mapping the ocean floor. So how difficult is it, like just about the measurement? Because as the ocean floor is very very deep, and yeah, so what are the challenges faced, and the possible errors there could be, like.
See, the challenges are first is uh, you need to get a research vessel which need to be available and that can survive the harsh weather condition in the open sea. Okay, and then when you go to the open sea, if everything was okay, then you need to get this drilling core drilling machines. Okay, which comes very costly because it has to go down and reach the ocean floor. Okay, so and then you will be getting uh, this different living organisms moving around. They try to deflect the uh, s- this we generally use this sonar technique as well, which gives the sound waves, okay, to
Yeah.
the earth, to the ship. So they are also like place some problematic when we are going for these kind of drilling project. And then the weather condition. Okay, so weather is always very different when it is in the open sea.
Okay. There were other two questions. One about, as you mentioned, whether there was one question in the beginning, which said, are these continents moved due to some kind of tornado or cyclones? I don't know whether it was related to weather or similar kind of processes in the earth that he's talking about.
Huh.
So that was one question. There is another question. Which instrument do you use to measure magnetic anomalies?
Magnetometer.
But what are the kind of uh, the precision units, the sensitivity of these instruments?
Okay. I sorry to say, but I have I can't recall the exactly like what are the corrections which we need to do for magnetic
Okay,
anomaly.
okay, fine.
One is though we have to first see the declination of the magnetic field with
Right.
the 11-degree ka declination, that we need to first correct it. And what are the other corrections that I have no idea right now.
I had two questions. One is, I mean, all these names, the different authors give, obviously, that Rodinia or Pangea. So, which are the people who have contributed, that is the major contributions to, in this model, to put that these are the people who have, I mean, these are the names which are given.
So
And yeah,
Alfred Wegener is the one who told about the Pangea. Okay. After Panchea, people, there are like other groups of people from mostly from Europe and America. They came together, they started understanding, and even the Australian geologists later on, they came up and they spoke about Rodinia. Otherwise, before Rodinia, people were knowing only one supercontinent, that is Pangaea, which was given by Alfred Wegener.
okay. Uh, Also, as you see this, I mean, two questions related to that. That as you see this continental drift, at some point you see that Sri Lanka appeared, uh, as the Indian plate moved towards the north.
Correct.
So, does it mean that it is still growing? That is one thing. And second thing is, is the age of rock that you discussed yesterday is the method to independently decide how the seafloor has spread?
Not independently. So people started dating the rock, and mostly the spreading was because of this reversal of the magnetic field. So people came to know more about spreading of the seafloor first by the magnetic field, and then when they started dating and then comparing with the magnetic field, they came to know like how much the reversal, like what was the reversal time period, how much thousands of years it took for the Earth's magnetic to shift completely 180-degree. So that gave an idea about how the sea was shifting from the axis to the other side to far away of the axis.
So the reversal was already dated at some other place, and then they use that data here.
No, sir. So what they did is, from the crest or from the axis of the mid-oceanic ridge, so they traveled towards one of the coastline. Okay, the ship. So they collected, wherever like the just a minute. So where is this image? Huh. So see, so this anomaly which you are seeing here, so they collected a rock from this particular part. Then they collected a rock from this low intensity magnetic field ka part. Then they again collected a rock from this magnetic field part. And then they dated these rocks. And from that, they created this time scale by dating of this rock age as well as the magnetic field, how whether the magnetic field was a positive field or a negative field. From there, they came to know about this scale. They have not collected randomly from other places where the magnetic field is reverse. So they have taken along this course from the center till here.
Okay, there was one question by Sushmita Madam that
Hmm.
where in India these research is happening?
Okay, so for seafloor spreading, like for Indian Ocean, all kind of like whatever the research is happening for Indian Ocean is happening in National Institute of Oceanography in Panjim, Goa. And there is another institute again in Goa, that is a National Center for National Center for Antarctic and Polar Research. That is again, let's say, it's an institution under Ministry of Earth Sciences, National Center for Antarctic and Polar Research, and NIO, that is National Institute of Oceanography, is a CSIR institute. So this two institute, they completely work for ocean basin. So whatever, like from mineralization to biodiversity to tectonics of ocean floor, entire research is going in this two institute. And there are like there is another institute in Cochin. Even like few of the scientists, they also are working, but majorly the bigger projects are carried by this two organization, National Institute of Oceanography in Goa and National Center for Antarctic and Polar Research in Goa.
Thank you, sir. Before, I mean, we are going to make one important announcement. So before that, so please be in the meeting. Before that, Professor Shekhar, you may propose vote of thanks if there are.
Okay. So I would like to thank today's speaker, Deepak Sahu, for the wonderful lecture and answering all the questions about the anomalies and how the magnetic field is determined by geologists. So we physics only look at the magnets. So here was a bigger challenge for all of us to understand. Thank you, Deepak, and I thank all the participants also. Thank you.
Yeah, thank you,
Nice.
Professor Shekhar. On behalf of Wilson College and IAPT, we are making an announcement that we will be giving away the certificates next week. The recording of this program also will be uploaded next week on Wilson College channel, YouTube channel, also on IAPT's Mumbai YouTube channel. But an important announcement is about all participants are requested to send a write-up about your learning through this lecture series, and you can write it in the form of an essay with minimum 750 words, maximum 3000 words, and it will include various different points like something new that you have learned in the lecture series, some interesting feature that you consider as take home from particular lecture, area of planetary physics that you got motivated and you wish to take up for higher studies. So you have to write an essay and send that essay to physics@wilsoncollege.edu and cc to iapt.mumbai@gmail.com. We'll put this notice also on the WhatsApp group. And last date for this is 14 January. So before that, the lecture recording also will be uploaded so that you may be able to sometimes refer back to that as well in case you have noted down things, and organizers will select some of the best essays and also give prizes for that. Okay, so with this, I request Professor Michael D'Souza to conclude this lecture series.
Hello.
Yes, sir.
No, I'm very thankful that we had quite a few participants who sat through the entire lecture series, and it was been a very nice lecture series. All the diverse resource persons that we have really helped us understand different aspects of planetary science. I hope this has been a fruitful experience for everybody. And we wish to seeing many of these participants in further programs that we might jointly conduct between IAPT and the Physics Department of Wilson College. Thank you very much.
I also request Shamala Madam from IAPT, who is Mumbai Sub-Regional Council Treasurer, to speak as we conclude this program. Shamala Madam.
Hello. Hello,
Yes,
can you
ma'am.
hear me?
Yes, yes, ma'am.
Yeah, it was really a very nice lecture series. The speakers, all the speakers were very good, and we could really got chance to listen to different areas of planetary science. And I'm really grateful to you for arranging lectures even in the branch of geophysics. And all those lectures also were very well done. And I thank Wilson College on behalf of IAPT Mumbai Surgical Council for arranging this such series. And we are looking forward to have a collaboration with your college for many more such programs. Thanks a lot.
Thank you, madam. Thank you, everyone. And we will end this meeting here.